Hello everyone, this is Team 9's midterm project on content-based image retrieval. Our team consists of Enos, Batu, and myself, and essentially our implementation will try to demonstrate how computers can search for images based on their visual content rather than textual descriptions. For a brief background introduction, content-based image retrieval, or CBIR, addresses the fundamental issue of searching visual data without semantic annotations, and the exponential growth of digital imagery has outpaced the manual annotation capabilities, creating a necessity for automated content analysis systems. For CBIR systems, they extract computable features directly from the image pixel, enabling similarity-based retrieval without the need for human intervention. And there is a semantic gap between low-level features with high-level concepts, and this remains a challenge within this field. And although deep learning and machine learning has addressed this issue, for our approach, we're going to focus on using low-level color features simply because it is a good starting point to understand CBIR principles. For the two papers that helped us with our implementations, the first being an intro to content-based image retrieval in 2013, this survey provided a taxonomic framework for CBIR features. The paper categorized visual descriptors into color, texture, and shape domains, each with distinct properties and computational characteristics. The color histograms, the insight here is that color histograms exhibit rotation and translation invariance. However, they do lack spatial encoding. Texture descriptors like co-occurrence matrices, they capture local patterns, but they require careful scale normalization. And for shape features, they provide object level discrimination, but they need robust segmentation. So this paper kind of helped us prioritize color features because it's efficient and effective in the image retrieval task that we're trying to do. The next paper is a work on MPEG-7 dominant color descriptors. And here the authors address the quantization problem in color-based retrieval. And their analysis reveals that threshold-based dominant color extraction produces very inconsistent feature dimensions, which complicate similarity computation. So by fixing the descriptor at 8 dominant colors and employing HSV color space, they achieved a significant performance improvement where the precision increased from 30 to almost 90%, while recall improved from 46 to 76%. So this paper and the authors, they demonstrated that constraining the feature dimensionality can almost like ironically improve retrieval accuracy by ensuring consistent metrics that are comparable. So this paper helped us in our implementation when we implemented the use of a fixed 64-bin histogram rather than other strategies. And for our method, our process had two main phases. First is for the database building. We take our 100 images, convert each from RGB to a 6-bit color representation, giving us 64 possible colors, extract the normalized histograms, and store these as a 100 by 64 matrix. Then during the query processing, We'll have the user select the image, extract the features, compute the Euclidean distances to all the images in the database, sort or rank by similarity, and then display our top results. And this was shown to be very efficient for our approach. The first part of our implementation is essentially the color space quantization. So we have our function here implementing the scalar quantization, reducing each of the color channels from 8 bits to 2 bits through division by 64, and this allows each channel to be divided into 4 levels that we see here, and the final 6-bit encoding, combining the channels using bit shifting, giving our values here, and this gives us many benefits. The first being a dramatic reduction in our color space, which also leads to the benefit of making our system more robust to minor color variations or light changes, and also just simply reducing computational requirements. For the feature extraction, this is handled by our getHistCount function, which creates normalized histograms. So for each image, we count how many pixels fall into each of our 64 color bins, then divide by the total pixel count to get the relative frequencies. And this normalization is important because without it, a very large image, such as a 4K image, for example, would just simply outweigh like images that are like thumbnails. And yeah, without normalization, these differences would not be because of the content, but simply because of the size. And we want the same image with different resolutions to produce identical normalized histograms. For the distance computation, we employed the Euclidean distance formula, and we used it because of its theoretical properties. It satisfies non-negativity, symmetry, and also it just aligns with the perceptual color differences in this instance. And it also leverages MATLAB's vectorized operations, computing all the 100 distances that we're using here simultaneously through matrix subtraction and column-wise calculations. The other metrics considered were the L1 norm for robustness, cosine for angular similarity, and the quadratic form. But Euclidean's distance provided the best balance between the effectiveness and simplicity that we're looking for our normalized features. Here is our test query. We're using this specific image right here, where there's this image exhibiting a color distribution of high contrast for a certain type of ad. And below, the histogram analysis kind of reveals the primary modes between the bins 60 to 63, corresponding to the yellow and green pixels comprising, the majority of this image, and the remaining, the remaining modes appear in these bins. And this kind of just shows like the limited color palette we have with this image. So this should, once we tested, the retrieval system should successfully, identify other images that are very similar to this color scheme. And those that are not similar would not be considered in our top results. And move into those results. Here we see the top 20 retrieval results for our query. And our system does exactly as we expected from the histogram analysis, where the first result here has a distance of 0, meaning we found an exact duplicate of our image. From 2 to 10, the distances are below 0.07, meaning that we found variations of the same, as you can see, the same image or advertisement. So it shows that there is some robustness in any minor modifications that are done to these images. From 11 to 20, they include semantically different content. It could possibly share like the same color characteristics, but they're ranked this way due to the content of the images being different. So all in all, this shows both the strength of color-only features with these top results, and also the limitations of color-only features, where like here, the presence of what appears to be like the city images, it tends to capture like possibly the statistical properties of these images rather than the semantic content, which again goes back to the limitation of color-only features. So before we get to the demo and conclusion, the implementation successfully implemented a CBIR pipeline that processed our 100 images, and the 6-bit color quantization provided an effective balance between being computationally efficient and still maintaining the discriminative abilities. And our implementation correctly grouped visually similar images. And we also saw the limitation that color-only features, it misses out on the texture, shape, and other content of the images. And that leads to the future work possibly incorporating, having multiple feature types, maybe implementing feedback from the user interactions, or employing machine learning or deep learning features for better semantic understandings. But despite these limitations, our approach here demonstrates the fundamental principles of content-based retrieval. And here are our references. And for the quick demo, here is our database building. And here we're just setting up the directory paths, importing our images, scanning for the types that we want, reading the images, making sure it's in RGB format, converting them into 6-bit color space, and using the getHistCounts function to generate a normalized 64-bit histogram. And then the result is stored in our db.mat file, which is the 100 by 64 matrix. And then for our query processing, in our cvir.m file. Here uses the kind of similar process from the database script. Yeah, we select the image we want to test, and then it'll display the visuals of our query. And just for a quick demonstration, that same image, and here are the results that we saw earlier. And once again, we see that images with lower distances that are closer to 0 are more similar to the image that we selected. And that is it. Thank you for your time and attention.